In this video, we're going to be bringing together everything that we've learned so far with our step counts, our growth shapes, our best, worst, and average case scenarios, and we're going to compare our searches and sorts that we've been implementing all year. In my last video, we did already take a look at insertion sort, and we discussed linear and binary search algorithms as well, while looking at the different types of inputs that can affect them during execution time. Let's continue this discussion with this very simple domain of searching. And let's just draw ourselves a little table to get started. So we have a binary search. Actually, I don't know why I would start with binary search. Linear search over here. And binary search over here. And I am going to make this into a little table. All right, 1 and there. Okay. Now, linear search should need absolutely no reminder on implementation. If we have n elements, there we go, we found that worst case, our runtime, I'm actually going to write out, because we're talking about time, I'm going to do a capital T. I'll do it in a different color also. T worst was n elements, right? We know that that was the worst case scenario over n elements. I guess I can even be n steps. Yeah, let me rewrite this a little bit here as you're all trying to follow along. I'm sorry. Steps. There we go. It'll be n. Perfect. But we also have our best case scenario, T best. And in our best case scenario over n elements, we found we could get a runtime of 1. Let's do the exact same now for our binary search, which we also saw in my last video. We saw that the worst possible scenario with binary search looking for a target element was going to take log base 2 of n steps. And our best case scenario was once again finding it in the very first spot and hitting that constant runtime 1. Let me put a line right here. We end up with a little bit of a table inside of a table, so it's a little bit of a 3D case going on here. All right, let's just pull up a graph here that actually outlines these two worst case scenarios right here and right here. I've actually got these graphs right here so that we can really outline these worst case scenarios. What we can see going on here is that at a small n value, like tiny on this side of the graph, we can see that linear search works just fine. Doesn't take very much time at all. It's no problem, right? We can see that this is going to be a low number and a low number, and that we should be good to go. This is a real proper graph. If I actually were to graph what an n algorithm would look like. If there are n steps for n elements, it's going to go in a straight diagonal line like this. What we can also see is that at a certain point, our n is going to get too large for this to still be true. At a certain point, we see that binary search dominates. And one of the best ways to showcase this is if I just pick up my binary search graph and I just place it right on top. We can even see that with this graph, there is a spot here where my linear search, right down here, is potentially faster than my binary search. And something like that could actually happen, and we'll talk more about it a little bit later. But what we do see is at a certain point in time, and that's off a little, right here. At a certain point in time, our binary search, right here, begins to dominate in time, and there's just no looking back. Now, I'm not going to get into the formal definitions of our asymptotic notation. That is something that you will see in future years. However, this is the key point. At a certain point in time, as I've shown here in blue, there will be a certain value, often depicted as m, like for mom, where we can say for certainty that one algorithm is going to grow more slowly or more quickly than others. Now let's switch domains and compare the sorting algorithms that we've been working with. And this is where the growth shapes start to matter even more. This also, as we saw in the previous video, noted that input order started to matter in really interesting ways as well. Let's get 3 algorithms that we've seen drawn into a table here now. Thank you to the magic that is video recording. All right, we have already seen insertion sort's behavior. So this is just going to be a quick reminder for insertion sort. If we're going to be talking about the number of steps, we have those 2 different cases again where we can say worst case. Oh, we'll write it the same as we did before. T worst case. And we saw that the worst case for insertion sort was a fully reversed array, like in sort, reverse sort or order. And this landed us with approximately n squared steps for an input size of n. We also saw our best case scenario right here, and our best case scenario was n, which is awesome. This is when our list was already or nearly already sorted. What we can see here between n and n squared is a big difference, and insertion sort is very sensitive to input order. How does this compare to the other 2 sorts that we've already seen in the course? Let's compare that to selection sort, because selection sort, while technically is explained as an n squared algorithm, does work differently. We know that selection sort will repeatedly scan the entire remaining unsorted portion of the list to find the smallest element, and then it does a swap in place. So every single run, we have a bunch of comparisons that we make, and then a single swap. Here's the key observation. Regardless of the order of your data, selection sort will always do the same number of comparisons. It doesn't matter. Try it out on paper. Sorted order, reverse sorted order, random. It will always do the same number of comparisons and 1 or potentially 0 swaps. That does not change. It is much more robust to the order and general distribution of your data. So what that means is in all scenarios, T worst, T best, and I can even say T average here really easily, it will always be an n squared algorithm. So while insertion sort can benefit from good input order, selection sort just doesn't care. This makes selection sort very predictable, but just not especially fast. It does give us a really good reason to know why we might want to do an insertion sort when we are physically sorting books in a library, because hopefully the shelf is already or nearly already sorted, not a selection sort. Now let's contrast both of these with merge sort. Merge sort actually doesn't look at the data order at all, like the same as selection sort. It doesn't care. A reminder, with merge sort, we were splitting our list in half, and then we recursively sorted each of those halves, merging those sorted halves together. This gave us that structure where we saw a log n level of splitting with n work at each level. And overall, we found ourselves having n log n steps. This was true in every single case, regardless of the data order, similar to selection sort. We have a T worst, a T best, and a T average, all of which align nice and robust regardless of input data, n log n. Oh, my table is a little too tiny over there, but that's okay. There is no special best case or disastrous worst case. We get really steady, predictable growth. So let's just take a look at this table here and figure out what the heck we've learned. What we've seen is that both insertion sort and selection sort in their worst cases have what is known as quadratic growth, right? They have quadratic worst cases, n squared. Insertion sort is adaptive. It can get faster when our data is nearly sorted. And in scenarios where we need a real quick sort with very low overhead and our data is almost sorted, this might be the sort we want to use, like in a library. But selection sort is non-adaptive, right? It's going to do the same work no matter what. If we don't know anything about our data set at all, we have no reason to be choosing insertion sort over selection sort. Selection sort will always be the same. Merge sort, meanwhile, completely escapes that quadratic space, right? We come down. We're no longer in that n squared world. We are in n times log n. Hopefully we can sort of, sometimes I feel like people see those numbers and like get a little confused, but like n times log base 2 of n is what we're talking about over here. And when we say n squared, what we really mean is like n times n. So hopefully we can see that n times log base 2 of n will always take less time than n times n. So when I say we escape that n squared world, it's because the growth of merge sort will always be fundamentally smaller than either of the worst case scenarios for insertion or selection sort. Let's just draw this as a graph. What we can see here is a graph where we're charting the worst case number of steps as our input size is growing. What I've got going on right here is an insertion and a selection sort, both of which, as we saw in the table above, have that n squared worst case number of steps. So I couldn't really draw them directly on top of each other, but like these are supposed to be representative of an x squared quadratic graph, right? Going basically straight up. We get that half of the parabola there. Now what we see is our merge sort. My line is actually even maybe a little bit too linear, but it's like there's a little bit, no, that's still too, it's like not an easy line to draw. I should have just found a picture of it. There we go. It's not like n, right? But it is still going to grow. What we can see with our merge sort line, which is the one I've got right down here, is that regardless of what's happening down here in this tiny little space of small input sizes, we see the payoff almost immediately as our input size grows. We see that merge sort at n log n will be significantly faster because it's growing in time at a slower rate compared to insertion and selection sort, right? What we're talking about is slow growth, fast algorithm. Let's just put a few numbers here on paper to really solidify this, because this is often where students get tripped up. Let me just draw 2 panels again. We're going to do an n equals 20 and an n equals 2,000. Oh, 20,000, sorry. So for small lists like n equals 20, the difference between n squared and n log n might be tiny. For example, n squared is 400 here. But n log n of 20 is only going to be about 86. And on our computer, both of these are honestly probably fast enough, right? In practice, one might be a little bit faster than the other, but in reality, for tiny numbers like this, 486 steps, like our computer can do thousands of steps per second. Especially nowadays, computers are so powerful. So we don't really have to ever worry about that. And honestly, even for a worst case scenario insertion sort on a small list, it's still possible that it could go faster than one of your other options, just because it's easy to write and there's very, very low overhead as well, meaning Java doesn't have to manage and work very hard the way that it would if you were doing, say, merge sort and relying on recursion and the runtime stack. But what we do see is at scale, constants and simplicity matter greatly. What we see is when n begins to grow. And you can absolutely plot this, right? We can plot this on a graph between n and these functions. These are like the most basic graphs that we can possibly plot. If we imagine now we've got 20,000 and we multiply 20,000 by itself, right? We're going to do that n squared. We get, I don't know, like 40 million. We get a really big number, right? We get like 40 million, something crazy. But if instead we look at our alternative sorting algorithm for 20,000 elements, like merge sort, what do we get instead? Well, we're going to get something like 285,754. These are approximate, right? Well, I guess the first one isn't approximate, but these ones are. Logs are approximate there. Yeah, that still maybe feels like a big number, but it's like considerably less than 40 million, right? All of the sudden, insertion sort loses its advantage. Selection sort becomes painfully slow, and merge sort is the only one that keeps scaling gracefully. And this is why large-scale software does not rely on these quadratic sorts, such as bubble sort, insertion sort, or selection sort. They're still really important for us to understand fundamentally, and in our use cases, they're often more than enough, and we are all about lazy, smart decisions. But in the real world, that's not going to be enough. It's also important to remember that just because I'm showing you these numbers right now in red as worst case, this isn't the only option. We also have a best case option. And a best case option for, let me relabel these. Worst case options were n squared or n log n. Best case options will be n squared or n log n, depending on what we're looking at. So if we were talking about an insertion sort, we end up with a best case scenario of 20 here. We also have a best case scenario of 20,000 here. Sorry, 20,000. Now, that is significantly better, of course, than 40 million. But the gap between these two runtimes is quite large, which makes it not as reliable. We don't know necessarily what we're going to get out of it, right? If the input order matters, we can get something good out of insertion sort. But it's nice that selection sort and merge sort are robust and they don't need those cooperations at all. That is the trade-off. Doing a merge sort in the library shelves would be chaos and unnecessary and save us no time. Our domain matters greatly. So here's our newly refined picture. We can see that insertion sort is fast on nearly sorted data, but it is terrible in the worst case. And we can see that selection sort is terrible in all the cases, but at least it's predictable and it is incredibly simple to implement. And then we have merge sort. This one is consistently efficient, even for huge inputs. And there are lots of other sorting algorithms out there. This is a really big topic. We're going to see another one in my final video set next week. When we look on our computers, our small input sizes often hide the differences between these sorting algorithms. But as we hit big data and larger input values, these differences between these algorithms is magnified. So at this point, you should already be able to make an informed algorithm choice. You understand these growth shapes and how input order matters. We can also see why an n log n algorithm would dominate its scale. In my next video and final video set, actually, we are going to add quicksort into this comparison. And it's another sorting algorithm that we can see really a couple of interesting use cases with. We're going to see how an algorithm can be extremely fast in practice, like extremely fast, but it also has a very surprising and dangerous worst case. We're going to be able to put all of our ideas together and keep moving through all the neat algorithms and choices that we get to make. Thanks everyone, and I'll see you in that video.